Okay, folks, I can see we just hit 1 minute after the hour, so we're going to go ahead and get started. My name is Matt Thomas, and thank you for tuning in to the USGS Landslide Hazards Seminar. This meeting is hosted by the Landslide Hazards Program and co-organized with contributions from Stephen Slaughter and Jamie Kostelnik. And for those of you that are new to this meeting, you have the ability to submit questions via the chat window or to use the raise your hand feature in combination with your microphone and video camera. We're going to wait until the end of the presentation to take questions. So in the meantime, please just do your best to make sure your microphone is muted when you aren't intended to speak. Luke, I'll go ahead and turn it over to you for today's introduction. Thanks so much.
Thanks everyone for being here. I'm very happy to introduce today's speaker, Olivia Hoke, who is currently with the USGS Landslide Hazards Program in Golden, Colorado. Before that, she did a BA in Earth Science at Vassar College and actually did a senior thesis focused on sediment transport in coastal settings. Then worked for a few years as a gemologist with the GIA in New York. And then I met her in 2019 when she came to the University of Arizona to get an MS in geosciences, and I had the pleasure of being her advisor. She graduated in spring of 2021 and did a lot of great work looking at post-fire recovery, which she's going to talk about today. And I should mention that she did essentially all of this in the midst of the COVID pandemic, which I'm sure you all know makes it challenging to do a number of things, including logistics of field work, which Olivia handled quite well with multiple field sites in 3 different states. So, one other warning, if you've ever done field work with Olivia, you'll know that she's pretty quick, even on those super steep slopes. So make sure you put a couple extra heavy soil samples in her pack when she's not looking and try and slow her down. So anyway, take it away, Olivia.
Thanks, Luke, for that introduction. So today I'm going to be talking about how landslides recover from the effects of a wildfire and how those changes impact the potential for debris flows in recovering burned areas. And I'm hoping there won't be any issues with my audio or the PowerPoint today, but if there are, I'll try to keep an eye on the chat and hopefully you can let me know. So a lot of what I'm going to be talking about today is in this JGR article by myself, Luke McGuire of the University of Arizona, Ann Uberg of the Arizona Geological Survey, and Francis Rengers of the USGS. So wildfires in the western United States have been increasing in frequency and severity. This map shows the total area burned in the past 5 years, not including our 2022 fire season. So there is a substantial area that is in some stage of recovery from the effects of a wildfire. And wildfires can affect the hydrology of a landscape. Fires remove above ground vegetation, which can reduce the ability of the canopy to intercept and store rainfall. Fires can lead to a reduction in surface roughness and can affect soils. Fires can decrease the soil's capacity to infiltrate water through fire-induced hydrophobicity, soil sealing, and the influence of hyperdry soils, among other things. And these changes to the landscape increase the potential for infiltration excess overland flow and for debris flows. So there are 2 primary mechanisms of debris flow initiation. The first, which is pictured on the left, is when the soil saturates, resulting in shallow landslides. And the second is when runoff concentrates on the surface and entrains sediment, initiating a debris flow. And in this presentation, I'm going to be focusing on the debris flows initiated by water runoff. Runoff-generated debris flows are often observed on steep slopes the first year following a fire and pose a risk to roads and other infrastructure. In steep watersheds, the potential for runoff-generated debris flows, which is this blue line in the schematic, is highest following fire and reduces over time as the landscape recovers. However, the length of time required for substantial reduction in post-fire debris flow potential and how those potential change from one environment to another is not well understood. Rainfall intensity duration thresholds, which define a critical rate of rainfall over a specified duration needed to initiate a debris flow, are often used to assess post-fire debris flow likelihood. Rainfall intensity duration thresholds have been empirically derived using past debris flow events to define a rainfall over which debris flows are likely to occur. As most debris flow events informing these empirical thresholds were within the first year following the fire, these thresholds are most applicable the first year following the fire. And the USGS also recently began reporting a year 2 threshold, though there are a few number of year 2 data points, so there's greater uncertainty in this year 2 number. So a recent study found a slope-dependent threshold of dimensionless discharge for runoff-generated debris flows. This dimensionless discharge threshold is supported by past experimental and field-based results. And dimensionless discharge, which is this Q star term, is the discharge of water non-dimensionalized by the median grain size of sediment in an incipient debris flow. If the dimensionless discharge is below the threshold, then water-dominated flows are likely. And if the dimensionless discharge is above the threshold, then debris flows are likely to occur. Another way to think about this is that for a given slope and a given grain size, there is a discharge of water that we can expect to initiate a debris flow. So our aim was to assess how different attributes of landscape, including vegetation, soil, roughness, and grain size, change over the period of recovery. When we combine these with a hydrologic model and the dimensionless discharge threshold, we hope to determine how the potential for debris flows changes over time as the landscape recovers. Finally, we will also gain an understanding of how different mechanisms of recovery impact debris flow potential over the period of recovery in recently burned areas. So this study builds on past work focusing on runoff-generated debris flows in 3 burned areas, which provide a baseline for hydrologic and geomorphic conditions immediately following the fire, which is crucial for assessing post-fire recovery. The first is the site of the 2018 Buzzard Fire in western New Mexico. This fire burned in May 2018 in the Gila National Forest near Reserve. This region is underlain by Oligocene basalt andesite lava flows and tuff. Hill slope soils are silt loam, and vegetation in this region consists of ponderosa pine and Douglas fir. There were 12 watersheds monitored by McGuire and Newberg directly following the fire, who also assessed vegetation and soils for the first year following the fire. And 8 of these 12 watersheds were unconfined soil-mantled swales, while the remaining 4 were channelized. And this region of New Mexico receives about half of its annual precipitation in the form of the North American monsoon from July to September. The second site is the 2017 Penal fire in east central Arizona. The Penal fire burned in May 2017 in the Tonto National Forest near Globe. The Penal Mountains are composed of protozoic metasedimentary and diuretic rock, which is exposed in the channels at this site. Hill slopes are sandy loam, and vegetation at lower elevations is primarily chaparral and desert shrub, while higher elevations is a oak and mixed conifer forest. At the site, we build off previous work that characterized the year 1 debris flow activity and soil and vegetation characteristics. And the rainfall in this region is similar to that at the Buzzard Fire, where it receives high intensity rainfall from the North American monsoon in July, August, and September. Lastly is the Fish Fire, which burned in June 2016 in the San Gabriel Mountains in Southern California. The San Gabriel Mountains are composed of granitic and metamorphic rock, which is exposed on hill slopes as bedrocks and as highly weathered saprolite. This, combined with the steep slopes, promotes dry arrival and loads the channels with fine sediment following the fire. Soils here are thin and are a sand to sandy loam, and the vegetation in this region is chaparral. We combined data from the first few years following the Fish Fire with data and model results from the nearby 2009 Station Fire, which had a similar lithology, soils, and vegetation in order to effectively assess how the landscape changed over the period of recovery following the fire. The climate at this site is Mediterranean with dry summers and cool, wet winters. And these 3 sites were selected based on the availability of baseline data and their spanning climate, lithologic, and ecological gradients. So we installed rain gauges and in-channel pressure transducers in order to assess the timing of flow. We also monitored debris flow activity, which we identified based on data from the pressure transducers and field verification of the debris flow deposits. We quantified changes to areas burned at moderate to high subtle burn severity for a period of 3 to 4 years following the fire at each site. We assessed vegetation at the plot scale, which you can see in these images up top. These are of the Fish Fire. And here you can see the vegetation transects that we used to assess vegetation cover. We also used remote sensing to assess vegetation regrowth. These lower images are of MODIS-derived leaf area index. These are also of the Fish Fire, and this lighter, tan color is lower leaf area index values, and this brighter color, which is outside the burned area, is a higher value of leaf area index. We used ecosystem-specific relationships between leaf area index and canopy structure to quantify canopy storage capacity at each site over the period of recovery. At each site, vegetation cover was lowest the first year following the fire and increased over the period of recovery. By year 3, vegetation at the Fish Fire was highest among our 3 sites, followed by the Penal Fire and the Buzzard Fire. The variation among our sites may be due to different timescales of recovery among ecosystem types. And our monitoring period was insufficient to observe vegetation recovery. Leaf area index values were still below pre-fire values at each site. And I also want to mention that our field and remote sensing measurements are intended to reflect the conditions during the season of peak rainfall and the highest debris flow potential. So that's the summer at the Buzzard and Penal and the winter at the Fish Fire. And that goes for our vegetation measurements and also other field data. We collected mini-disc tension infiltrometer measurements in areas of moderate high soil burn severity to assess field saturated hydraulic conductivity and wetting front section head at each site. For those who aren't aware or familiar with these, wetting front suction head is related to the capillary component of soils, while saturated hydraulic conductivity is the infiltration rate when soils are saturated. And so each year we collected about 15 to 20 measurements of each. We also determined the times of statistically significant changes in soil properties from one year to the next. At each site, suction head is lowest in year 1 and changes or increases in subsequent years with significant year-to-year changes between year 1 and year 2. Trends in field saturated hydraulic conductivity are more variable among sites. In many conceptual models of soil recovery in recently burned areas, generally saturated hydraulic conductivity is lowest directly following the fire and increases monotonically with time since burning. And the Buzzard fire followed this trend the best out of our 3 sites, where the median saturated hydraulic conductivity increased with time since burning. And at the Buzzard, the only statistically significant changes were observed between year 2 and year 3. At the Fish fire, median values of saturated hydraulic conductivity increased from year 1 to year 3, and the median value decreased in year 4. And there was no significant changes in saturated hydraulic conductivity observed over the 4 years at this site. The Penal fire follows a different trend. The saturated hydraulic conductivity was highest directly following the fire and decreases over time with significant changes between year 2 and year 3. And measurements of unburned saturated hydraulic conductivity or at unburned areas at the Penal site are around 19 millimeters an hour. So that's like about here. So we can interpret this trend as a return to pre-fire levels. And the Penal fire may have some natural hydrophobicity, which is destroyed during the fire, and that can sort of account for this trend that we're seeing. I think it's also noteworthy that significant changes in wetting front section head occurred between year 1 and year 2, while significant changes when present in saturated hydraulic conductivity occurred between year 2 and year 3. And this may suggest differing timescales of recovery for different soil properties. So we quantified a watershed scale effective saturated hydraulic conductivity and suction head through a model calibration procedure where we compared a modeled hydrograph with observed flow data from the in-channel pressure transducers. We found the effective watershed scale saturated hydraulic conductivity was lower than the mini-disc-derived point scale values each year at every site. The ratio of watershed scale to point scale saturated hydraulic conductivity was on average 0.92 at the Buzzard, 0.51 at the Penal, and 0.68 at the Fish fire. The lower values at the Penal and Fish may be related to the presence of bedrock at these sites, which could lower the effective saturated hydraulic conductivity. While at the Buzzard, which had a ratio of closer to 1, bedrock was more limited at the surface. Also, the variation between the sites could be due to spatial heterogeneity in soil properties among the sites. We used a similar model calibration procedure to estimate watershed scale values of hydraulic roughness. As the photos indicate, the hydraulic roughness was low in the first year following the fire at each site, whereas a Manning coefficient at or below 0.1. And by year 3, changes in vegetation and grain roughness had substantially increased hydraulic roughness, with the largest changes observed at the fish and Penal fires. At the fish fire, we believe roughness returned to pre-fire levels by year 2 based on modeling done at the nearby station fire. And while we don't have pre-fire estimates of roughness at the Penal and Buzzard, we don't believe that these sites returned to unburned pre-fire values by the end of the monitoring period based on the values for hydraulic roughness we would expect in unburned forests of these types. Finally, we quantified the grain size of sediment entrained by a debris flow. In order to quantify median grain size, we sampled the matrix material of undisturbed debris flow deposits when present. At the fish and Penal fires, the median grain size was very small in year 1 and increased by nearly an order of magnitude by year 3 at the Penal and a factor of 2 at the fish fire. In the photos here, you can see the temporal changes in grain size in the channel at the fish fire. On the left is the channel at the fish in year 1, and by year 3, you can see that most of the fine, easily mobilized sediment has been removed. At the Penal, cobbles, boulders, and bedrock were exposed in the channel following year 1, indicating that the finer material was mobilized and exported from the watershed, leading to a coarsening of available material. At the Buzzard fire, the median grain size did not change over the 3-year period of recovery following the fire. Debris flows at the Buzzard eroded through thick colluvium, sometimes creating gullies around 2 meters deep. And this suggests that the source material for the debris flows did not change at this site over the period of recovery. And variation among sites may be due to differences in lithology, in soil thickness, and in sediment transport processes at each site. So we've assessed how soil, vegetation, roughness, and grain size change over time in recovering burned areas, but we're interested in debris flow potential. So by taking these measurements, we constrained by field data collection, remote sensing, and calibrations, we can estimate rainfall thresholds for debris flow initiation. By integrating these measurements into a hydrologic model, we can test different designed rainstorms with known rainfall intensities and determine which rainfall intensities result in dimensionless discharge above the threshold, thus determining a rainfall threshold for debris flow initiation. For example, we selected a basin burned primarily at moderate to high soil burn severity at the Buzzard fire and modeled dimensionless discharge given the topography of this basin. We input a storm with an I-15, which is the rainfall intensity averaged over a 15-minute period of 25 millimeters an hour. The dimensionless discharge is below the threshold for debris flow initiation. And this dashed line is the slope-dependent dimensionless discharge threshold, and this solid line is the modeled dimensionless discharge. We can try with an I-15 of 30 millimeters an hour, and the dimensionless discharge is still mostly below the threshold. At an I-15 of 35 millimeters an hour, the modeled dimensionless discharge is above the threshold, and a debris flow would likely initiate. So we've determined that the rainfall threshold for this basin is an I-15 of 35 millimeters an hour. We selected one basin at each site and determined the rainfall threshold for debris flow initiation each year following the fire. And here are the results for rainfall thresholds at each site over the period of recovery. As you can see, the rainfall threshold for debris flow initiation was lowest at each site the first year following the fire and increased over the period of recovery. The smaller, darker gray squares, like these little ones, represent the thresholds given a central value for each parameter, and the lighter gray bars represent the possible thresholds given variation in some of the parameters. So these larger gray bars. This way, we end up with a range for the estimated thresholds. We can compare the rainfall thresholds to site-specific rainfall recurrence intervals. Here we have a 1-year recurrence interval storm. You can look at a 5-year recurrence interval storm, a 10-year recurrence interval storm, and a 25-year recurrence interval storm. At each site, a 1-year storm is capable of producing a debris flow at each site. By year 2, take the 5 to 10-year recurrence interval storm to initiate a debris flow, and a 10 to 25-year storm may be necessary to produce debris flows by year 3. The trend of sites with higher rainfall thresholds also having more frequent high-intensity storms, by which I mean the Buzzard and the Penal have higher rainfall thresholds and also have higher, more frequent intensity storms. And this suggests a link between the climatology of the region and the debris flow initiation thresholds. And I should have pointed out the scales for each site is different. So we can compare our modeled thresholds to observations of flood and debris flows at all the monitored basins. The red X's indicate a debris flow and the blue circles indicate water-dominated flow. And in general, the modeled thresholds agree with the debris flow observations, all but one debris flow at the Buzzard, red X down here. All but that one were at or above the threshold. And at the Penal and Fish Fire, all of the debris flows were at or above the modeled threshold. We can also compare the model results with empirical thresholds based on debris flow observations, which are these yellow stars. At the Buzzard Fire, the empirical threshold is within the range of our model estimated thresholds. However, at the Penal and Fish Fires, the empirical thresholds are higher than our model estimated thresholds. Some of this deviation could be attributed to our models being based on one basin, which we've assumed a moderate to high soil burn severity, while the empirical thresholds are based on observations from multiple basins, which have a mosaic of burn severities and are burned at some portions are moderate high and other portions are low. And because hydrologic impacts often scale with soil burn severity, we might expect basins with a higher proportion burned at moderate to high soil burn severity to have lower thresholds compared with those that are have a portion burned at low soil burn severity. Also, among all 3 sites, I think there are 6 debris flows collectively after year 1. And this reduction in debris flow activity is due to a combination of increased rainfall thresholds and temporal variation in rainfall that's above the initiation thresholds. For example, year 3 at the Buzzard, there are no storms above the year 1-year recurrence interval. And if anyone was in the Southwest in summer 2020, that's this year, and it was a particularly dry monsoon. And I think this also illustrates the challenges with using empirical thresholds beyond year 1. Also notably, in year 3 at the fish fire, there was a storm with a 10-year recurrence interval, I-15, that did not initiate any runoff-generated debris flows. However, this event did result in many shallow landslides within the site of the fish fire, and this suggests a potential shift in mass wasting processes over the period of recovery. And this event is described in this publication. So because these thresholds were derived using a modeling framework, we can assess what the thresholds would be if the conditions were different over the period of recovery. For example, we can compare what the year 2 and year 3 thresholds at the buzzard would be if there was no recovery of the soil, which are the blue bars, compared with the observed conditions, which are the gray. We can also simulate the threshold with no recovery of canopy interception, the threshold with no change in hydraulic roughness, and the threshold with no change in the grain size of sediment entrained in a debris flow. Through this analysis, we can assess the contribution of each parameter to the model change in threshold, which is shown on the graph on the right. Over the period of recovery following the fire at the buzzard, changes in soil infiltration capacity were of primary importance to increases in the threshold. The changes in soil infiltration capacity from year 1 to year 2 at the buzzard led to a 20 millimeter an hour increase in the rainfall threshold and a 60 millimeter an hour increase in the rainfall threshold in year 3. Changes to canopy interception and hydraulic roughness contributed to a lesser degree, and changes to the median grain size did not play a role in changing debris flow thresholds at the buzzard fire. We repeated this analysis at the Penal fire and found that changes in grain size in year 2 and beyond at the Penal had the largest influence in changes to thresholds at this site, which is shown by these large pink bars on the right here. Changes in hydraulic roughness and canopy interception also played a role in increasing the threshold. Saturated hydraulic conductivity at the Penal, if you recall from earlier, decreased over time, and changes to the soil over the period of recovery actually promoted a decrease in rainfall thresholds in years 3 and 4. At the fish fire, changes in canopy interception were of primary importance to increasing rainfall thresholds over the period of recovery. Hydraulic roughness, soil infiltration capacity, and canopy interception, as well as median grain size, all influence thresholds. The large role of vegetation at the fish fire may be related to the large changes in vegetation cover that we observed at this site. The fish fire had the highest measured changes in vegetation over the period of recovery among our 3 sites. And this also may reflect interactions between rainfall intensity and canopy interception, whereas a high intensity rainstorm may quickly saturate the canopy storage capacity, leaving the effect of canopy on runoff production negligible during major rainstorms. During a lower intensity rainfall, the canopy may intercept and store a greater proportion of the rainfall. This suggests a potential link between the mechanism of change in thresholds and the climatology of the region. So how can this inform what we should expect for debris flow likelihood over the course of recovery following a wildfire? Well, at our 3 sites, a 1-year recurrence interval storm was sufficient to generate a debris flow in year 1. And the greatest change in rainfall thresholds, which accounts to the largest reduction in debris flow potential, occurred between year 1 and year 2. However, there was no one landscape characteristic that we could attribute to the change in thresholds for all of our sites. Recovery of soil, canopy, median grain size, and roughness all played a role in decreasing debris flow potential. And this illustrates the degree to which recovery trajectories among burned areas in different environments, or vary among different environments, and highlights the need to consider site or ecosystem-specific approaches to post-fire recovery and temporal changes in debris flow potential. Also, the rainfall intensity duration thresholds for debris flows are not only dependent on site-specific factors, but also the conditions present over the period of recovery. If a site were to experience no debris flows the first year following the fire, say it was a particularly weak monsoon year and there was no storms above the year 1 threshold, how would we expect that to affect debris flow potential in year 2? Changes in hydraulic roughness, for example, are not only a function of time, but also influenced by the number and size of runoff producing storms. As fine sediment is removed from hill slopes and channels, grain roughness increases. And the similar is true for the median grain size. So in this scenario, we may expect the minimal change in roughness and median grain size in year 1 to have a reduction in year 2 thresholds, which would cause the debris flow potential to be elevated for longer following the fire. Similarly, if there's a scenario where there's a drought over the period of recovery and vegetation did not grow back as quickly as we might expect, this might serve to also prolong the period of elevated debris flow potential. Also, as fires become more frequent in recovering burned areas are more likely to be reburned before the debris flow potential has returned to its pre-fire levels. A portion of the 2017 Penal fire was actually burned in the 2021 Telegraph fire, which would be year 5 post-fire according to our calendar for the Penal. And although this region that was burned in both the Penal and Telegraph did not display greatly higher debris flow potential compared with the same 2021 regions that were burned in just the Penal, it is important to understand how reburns influence landscape recovery and debris flow potential. Finally, this study focuses on thresholds for debris flow initiation, which is only one aspect of debris flow hazard, and understanding how the properties of a resulting debris flow, such as debris flow volume or mobility, may change over the period of recovery would be necessary to fully understand the shift in debris flow hazard over time following a fire. So to quickly recap, a 1-year recurrence interval storm is capable of producing debris flows in year 1. A 5 to 10-year recurrence interval storm is capable of producing debris flows in year 2, and a 10 to 25-year recurrence interval storm may be required to produce debris flows in year 3. The greatest change in rainfall thresholds for debris flow initiation occur between year 1 and year 2 at our 3 sites, and recovery of different landscape attributes was primarily responsible for changes in thresholds at each site, with soil infiltration capacity being most important at the Buzzard, median grain size most influential at the Penal, and canopy most influential at the fish fire. Finally, thresholds are not only dependent on site-specific factors, but also the conditions present over the period of recovery. And thank you. I think we've got some time for questions.